So let's talk about the ethers. The ethers. Ethers are types of molecules that, for example, two alkyl group, for example, are attached together by a bridge of an oxygen molecule. These two R group can be both similar or they can be different and not similar. These R groups can be alkyl, they can be alkyl groups, or they can be aromatic groups. For example, they can be, you can have phenyl group that attach to, for example, one R group. So these are the shape or structure of the ethers molecule. About the naming of the ethers, about the naming of these molecules, about the naming, if we want to talk about, for naming you have, first of all, you have the oxygen, that is, that two groups are attached to the oxygen. We simply name each of the groups, and in the end we just add the ether. For example, simply when you have two methyl group that are attached to oxygen, you say methyl, 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 ether. Or better one, you can, because you have two groups of methyl, you just say dimethyl, dimethyl ether. That's the simple. Or for example, you can have this molecule. On this side you have methyl, on this side you have methyl, and on this side you have tertiary butyl. Tertiary butyl. So what is the name? We just say the name of the groups, and at the end, as said before, we just add ether. So tertiary butyl, methyl, ether. And the tertiary butyl is the first name because of the alphabetic relation. So you say tertiary butyl, methyl, ether. So that's the name of this kind of structure. Another kind of naming is that when you have not a simple group on one side, for example, in this situation you can say the name by naming the all the molecule as the substitution of an alkoxy group. Substitution of alkoxy group. What does it mean? For example, you can have this kind of molecule, O attached to metal, and other side is attached to 1, 2, 3, 4, 5, 6. You have hexane here, and on the other side the methyl. You can say the name like an alkoxy substitution. You take this side of molecule as the main, as the alkoxy, and you say methoxy, methoxy. So what is attached to the methoxy? It is hexane. So hexane methoxy, or that if you want to correct this name, you say methoxyhexane. So you name the ether molecule as the alkoxy substitution. That I mean the methoxy part. Alkoxy substitution. So about the some of the properties of ethers. First we can say ether molecules, the ethers, these kind of molecules can act as the acceptor for hydrogen bond. So these molecules can act as acceptor of hydrogen bond, and they are just focus, the ethers are not the donor, they are the acceptor, and because of that, because they are not the donor of the hydrogen bond, so the ethers are not miscible with the water, and they cannot form a powerful bond of hydrogen that can miscible with the water, that can solubilize with the water, and so on. Another thing about the ethers, properties of ethers, is that they can act as solvents, especially aprotic solvents. Aprotic solvent, it means that when you don't need the protic property of a solvent like water, like the solvents that can have hydrogen bond, that they can act as a protic solvent, when you don't need these properties, you can use the ethers, and they are aprotic solvents, and they do not interfere with some of the molecules that will be damaged by the protic solvents such as water. So that's the second property of the ethers. If we want to give an example about the protic and aprotic interference with the reactions, for example, imagine that you have a SN2 reaction. In this SN2 reaction, you have a central molecule, for example, that is attached to several other atoms. You have a nucleophile that want to attack the main molecule, and you have a leaving group that wants to exit from the molecule. In this situation, if you have an protic solvent such as water, for example, when you have protic solvent, not aprotic, this protic solvent will surround the nucleophile and make some interference with the nucleophile. That nucleophile cannot properly make its attack to the molecule, and the reaction will not happen. So in this case of SN2 reaction, you need an aprotic aprotic solvent, such as the ethers. So that was an example of the when you need a aprotic solvent instead of the protic solvent like water. Another thing about the properties is kind of comparison. For example, the ether molecule has lower boiling point in comparison to an alcohol molecule, and it is obvious because of the ability of the alcohol molecule to form a hydrogen bond, but we said that the ether cannot donate a hydrogen bond, and it can just accept the hydrogen bond. So the boiling point of the alcohols and ethers with the same mass, it is very important, with the same mass, the alcohol has a higher boiling point in comparison to the ether molecule. Another thing about the solubility of ethers, also in this case in comparison to alcohols, the solubility of the ethers and alcohols in water, so the alcohols and the ethers in water, they almost have same solubility, but here's a difference, and the difference is in alcohols with low molecular weight, for example ethanol, for example methanol, and these kind of simple and lower mass types of alcohols, these can freely or very highly solubilize in the water because of the hydrogen bond. But when you increase the mass, increase the carbons of the alcohol, the solubility almost is similar with the ethers in the water. Alcohol and ethers in high mass or in high molecular weights, they relatively have similar solubility in the water. Now let's talk about how we can synthesize the ethers. So synthesize of ether molecules. How we can synthesize these kind of molecules. First, the reaction name is called Williamson's ether synthesize. So the reaction name is Williamson ether synthesize. So the reaction is very simple, and in a simple way, Williamson ether synthesize is to synthesize the ether from an alcohol molecule. So from an alcohol molecule, and beside the alcohol molecule you have an alkyl halide. So for example, you can this kind of alkyl halide. You can have different types of halides, but in this case we say, for example, the bromine. But here's a problem, and when you add just these two molecules, the alcohol and the halide, alkyl halides, you can see that there is no reaction. And if you want to make this reaction, you should turn the alcohol molecule to a good nucleophile, and when you add some sodium to the alcohol, the result is this kind of molecule. This molecule named alkoxide. And now the alkoxide is a powerful nucleophile. And the alkoxide can attack these alpha carbon, because this alpha carbon has a partial positive because of the halide, and the alkoxide can attack these carbon, and you have the result of the reaction, that is ROCH2R. So now you have an ether molecule, and this called Williamson ether synthesis. So for the review, we turn the alcohol molecule to an alkoxide, and why? Because the alkoxide is a powerful nucleophile. Now the alkoxide attacks the alkyl halides, and the result will be the ether. Another thing about the Williamson ether synthesis is the type of reaction, and the Williamson ether synthesis is a kind of SN2 reaction. So for example, if you have a chiral carbon, so you can have the inversion of the configuration, you can have inversion of configuration, and so on. And another thing in SN2 reaction is the groups around, or substitutions around, the base molecule, and the substitution of the base molecule will affect the result of the molecule. And because of the Williamson ether synthesis is a SN2 reaction, we need a powerful nucleophile, that we make the alcohol and turn it to a powerful alkoxide nucleophile molecule, because it is SN2 reaction, and SN2 reaction needs a powerful nucleophile. So you have the effect of spatial obstruction. Spatial obstruction. It means the groups, the substitutions around the chiral or the carbon, whether it is chiral or not, the substitutions will affect the reaction. So here's the question: what do you mean about the spatial obstruction for the Williamson ether synthesis. So let's talk about it. So we said that the Williamson ether synthesis is an SN2 reaction, and because of it is SN2 reaction, so it has a special obstruction property. But what is a special structure for this molecule? Let's give an example to better understanding. Imagine you want to synthesize this molecule. So you want to synthesize this kind of molecule in the way of Williamson's ether synthesis. You have one way, for example, one way to from methanol is your alcohol, for example, and the tertiary butyl, for example, chloride, is your alkyl halide. So, and in this case, the oxygen of methanol can attack the halide, and you can synthesize this molecule. But here's another way, and you can use the methyl chloride and tertiary butanol, and this can, in this case, this OH can attack the methyl chloride. But in the practice, you see that this reaction does not happen, and this reaction can happen. Why? Because of the special obstruction. What is the special obstruction? It is that when you have a nucleophile in SN2 reaction, you need a space that the nucleophile can easily attack the gold molecule. And in this reaction, when this nucleophile wants to attack the molecule, you can see you have here 3 methyl group around the carbon, and you don't have enough space, so the reaction will not happen. But in the second type of reaction, when the tertiary butanol wants to attack the methyl chloride, you see here you have a carbon that is attached to a chloride and 3 of hydrogen, and there is enough space for attacking the OH to the carbon. So that was the special obstruction about the Williamson ether synthesis. Another interesting thing about the ethers is the hydrolysis of ethers. Hydrolysis of ethers means that you can split the ether molecule. You can split it to the particles that you made the ether of them. You made them. We talked before, for example, you can have alcohol that is attached or react with the alkyl halide and forms the ether molecule. Now you can split the ether to the alkyl halide and the alcohols with the hydrolysis reaction. How you can hydrolyze the ether? You should know that the ether molecule is very stable. Ether molecule is very stable in alkaline situation. So ether is stable in alkaline situation, but this ether is very, very sensitive and is not stable in acidic environments. So when you use some powerful acids such as HBr, such as HI, you can split the ether to the particles that the ether was made of, and you can have alkyl halide and alcohols with the hydrolysis of ethers.